Hey everyone, my name's Kanuka and welcome to my Actual 3143 project presentation. Starting off with a problem statement, the goal of this project was to predict whether credit card transactions are fraudulent or not based on both individual risk factors, so for example, an individual's age and gender, as well as the transaction characteristics. So for example, the transaction amount, as well as what was actually purchased. So quickly, a bit about credit card fraud. It actually occurs in two main forms. So firstly, either an individual's physical card is stolen and used in person, or secondly, an individual's card data is compromised and used online. This problem in particular is a supervised binary classification problem, and it's binary because there are two potential outputs. It's either yes, it is fraud, or no, it's not fraud. This data set is also extremely imbalanced, and I'll get to this in a bit more detail later on, but this will affect some of the modeling techniques we use. Moving on to the data source. Starting off with data collection, the data was sourced from Kaggle and contains simulated transaction data across a 2-year period. The data was actually provided to us in two separate files, a pre-split train and test file, but we aggregated this together, which resulted in 1.85 million rows or transactions and 23 features from 1,000 unique customers. In terms of data cleaning and pre-processing, all the unnecessary columns were dropped, and then new features were created using existing ones. So for example, one of our variables was a concatenated one, which included date and time and everything squished together. But we extracted separate features from this, such as month or time, to look at things like seasonality, for example. There were also no missing or NA values present in the dataset, so we didn't have to worry about any imputation. Here is a quick snapshot of what the data actually looks like. And as you can see, each row is a unique transaction with its own characteristics based on the transaction as well as the individual. A quick note on EDA, as previously mentioned, the dataset is extremely imbalanced, with 99.5% of the transactions being non-fraudulent and only 0.5% being fraud. As a result, techniques such as undersampling, which involves removing samples from the majority class, as well as oversampling, which involves duplicating samples from the minority class, as well as the use of metrics other than accuracy, were considered for our analysis to account for this imbalanced dataset. Now moving on to deep learning approaches. But firstly, the benchmark model was a very simple, very basic model, which assumed that there were no fraudulent transactions. The loss function here was a binary cross entropy one. And the second point here was that since only 0.5% of the transactions were fraudulent, this very basic model will have an extremely high accuracy of around 99.5%. And as you can see, the main takeaway here is that accuracy is not a good metric for this data set, so other ones will need to be considered. Moving on to our deep learning architectures, the first one was deep and wide with entity embedding. So our 6 categorical variables were first entity embedded and then concatenated with our other numerical inputs. This was then passed through a dense hidden layer and finally into an output layer with a sigmoid activation function for the binary prediction. The second architecture was a Bayesian neural network, which instead of using a point estimate for weights and biases, instead uses a distribution with a mean and a standard deviation for those values. This architecture also uses dropout, which essentially turns on and off random neurons in the training process. And once again, we see a sigmoid activation function in the output layer for binary prediction. Now looking at some of our preliminary results. So this was calculated before any hyperparameter tuning was done. We can also see that there are undersampling datasets here, undersampled using the near-missed algorithm, and oversampling datasets as well, done using the SMOTE algorithm. As you can see, the benchmark model has very high accuracy, as previously mentioned, but does very poorly on most of our other metrics. In contrast, the BNN model performed poorly across all metrics and will need a bit more fine-tuning. However, the deep and wide neural network with entity embedding had the strongest performance on all our metrics except for balanced accuracy and ROC. And for these two metrics, the deep and wide with undersampling actually performed the best. So overall, we can see this model is doing quite well. Something to note is that the balance accuracy, F1 score, and PRAUC, all those metrics are very suited to imbalanced data sets because they don't put as much weighting on the true negative predictions, which in this case is correct predictions for the non-fraudulent transactions. So those are the preliminary results, and thank you for listening and hope you enjoyed.